Uh, in this lecture, we will discuss about the concept of frequency domain analysis, or known as frequency response analysis. We all will know what about the frequency response analysis and why this frequency response analysis is required. And because already we have done the time response analysis, some part of the stability analysis by different methods already we have developed in the last series of lectures. I have already communicated. Now here the frequency response analysis means, for example, a system is given, say this is your GS, the transfer function of the system is given. Now here instead of any signal which is normally function of time domain, we will apply any signal, say RT equal to A sine omega t, right? So that is a sinusoidal kind of signal. If we apply, then we will get the response. That means the output of the system, we will get something output of the system which is known as the response. And as we are dealing with this kind of sinusoidal kind of input, so whatever we are getting, that is known as the frequency response. And for frequency response analysis, what we actually get is that these transfer functions GS is to be converted into known as sinusoidal transfer functions. So sinusoidal transfer functions means what? That means that is the function of frequency. So we know S is equal to j omega. As we know S is equal to j omega, definitely this GS will be termed like Gj omega. So once we get Gj omega, this will be your sinusoidal transfer functions, and this part is very much important because once you will get it, then only you can go for the frequency response analysis methods. So different methods we will describe, and by using the frequency response analysis, again we are going to get the stability of the system by certain measuring the parameters. So Gj omega will be that is a function of omega then. So function of omega means this is a function of frequency. And you see any functions which is written like Gj omega, see Gj omega, this is definitely one complex quantity, there is no doubt in it. And if this is a complex quantity, that means it will be having one real value plus one imaginary value. So we may call it Gj omega equal to, say, A plus JB, right? So that is a real value and one imaginary value in any complex quantity. So this is your transfer function in frequency domain, because this is the function of frequency and this is a complex quantity. So this complex quantity can be written like real and imaginary. That means once there is a quantity which is complex in nature, that means which is having say real part as well as imaginary part, that means it will be having one magnitude part and one phase part, right? So this is magnitude part and phase part. So what will the magnitude corresponding to this? Any transfer function which will be expressed in frequency domain, that is sinusoidal transfer functions, that must have to be written in the form of real and imaginary part, because that is a complex quantity. It must have real and imaginary. Maybe the real part is 0, but there must be the imaginary part. So this real plus imaginary part means this will be having magnitude and phase. So magnitude will be you can write a square plus b square, you see, and phase is tan inverse imaginary by real, all we know. That means tan inverse b by a, right? So this is the concept of analyzing this kind of transfer function. That means whenever we are going to get the frequency domain analysis, so what we have to do, we have to first get the transfer function in frequency domain. That means that is the function of frequency. Once you convert this into S is equal to j omega, because you know in the frequency case we have to consider the poles on the imaginary axis. That means if this is your S plane and this is your real and this is your imaginary, then everywhere the real part is 0. So S is equal to j omega is the equation of this imaginary axis, right? So according to that, you are getting one magnitude part and one phase part. And you see, whenever we will study certain kind of transfer function, we can find out this magnitude is a function of frequency and this is also the function of frequency. So what we will get this magnitude is itself is a function of frequency, and that phase is itself a function of frequency. So we can write this magnitude. This magnitude, this is a function of that means that is function of frequency, and also this phase part, that is the angle what we'll get, that will be a function of frequency again, right? So once this is a function of frequency and phase is also a function of frequency, what happens, that means you are going to apply certain kind of sinusoidal input with the different frequencies. That means if you want to vary the frequency, for example, the graphical presentation is like this. So this is your omega, that means frequency, and this is your magnitude. Once you vary the frequency, say from minus, for example, we are considering on this positive part 0 to infinite, say for example. So this is the complete range of frequency, that is positive frequency starting from 0 to infinity, and if I am going to vary this frequency, definitely there is a change of magnitude, maybe in any way, right? So we can plot actually the characteristics curve which shows the variation of the magnitude with the frequency. Similarly, we can have the same like structure for variation of the frequency with phase, because phase is also the function of frequency. So this may be like this, or whatever the different kinds of response we will get once the frequency is varied, simultaneously we are getting the magnitude and phase are varying. And by considering or observing this change of magnitude for a certain change of frequency, similarly change of phase for a certain change of frequency, we can get in which frequency range what is the magnitude and which frequency range what is the phase, and their relationship, how they are varying like this. So these are all in a single statement, we can call it as the frequency response analysis, right? So by observing the frequency response analysis, what is our main aim? Main aim is to get whether a system is stable or not. That means we want to observe system stability as a whole, right? So main objective, system or not, either system is stable or not. That means this is frequency response analysis is also kind of tool basically which is used to get the stability of any system. So frequency response analysis is a tool which is used to get a analysis of the stability. So stability analysis tool is this frequency response analysis. And why this frequency response analysis is required then? Because we have many tools to find out whether the system is stable in time domain or not. But the problem is that when we have analyzed the time domain stability for any complex system, if you can remember, for any higher order system, that means if the order of the system is higher, so it is very difficult to analyze the system. So difficulty arises, difficulty level increases. That means to analyze the stability of the system in time domain which is having a higher order, so it is very difficult. So in that case, what you have to go for? We have to go for another method. So that method is something frequency response analysis kind of thing, because in case of frequency response analysis, higher order systems can be easily analyzed to get whether the system is stable or not. And in practical situations, the maximum of the systems are normally higher order, and there are different techniques to by which we can get the system can be reduced by into a second order. That is the another course we will not discuss here. So thing is that the difficulty in the time domain section is overcome by using the frequency domain analysis, and we see the lower order system as well as the higher order system can be analyzed easily by using this frequency domain analysis or frequency response analysis tool. So now the question comes, what are the different tools available? Definitely this is the method, generalized method. So there are normally we will study here three kinds of tools. One is known as Bode plot or Bode diagram. This is one kind of tool which is used in the frequency domain to get the system stable or not. Second thing is that polar plot analysis, and third is Nyquist plot analysis, right? These are all, you can say it, graphical approach, because in the time domain analysis also there was the defined methods which are graphical and analytical, and here these three all are the graphical approach and very interesting method, and how the mathematics can be very easily be expressed by graphs, and from the graphs you can easily observe whether the system can be stable or not, and in which frequency range the system can be made stable, and after which the system can be made unstable. These are the all aspects which are going to discuss in this chapter, that is frequency domain analysis. Now for the first part we will discuss the Bode plot, and the next subsequent lectures we will discuss about the polar plots and Nyquist plots and the different problem solving methods, how we will solve the problems, right? So now here we will start with the Bode plot. So Bode plot, by the name you see, this is the name of one of the scientists or mathematician who have discovered this kind of this graphical approach by which the system stability can be analyzed. So Bode plot is a frequency response analysis again. So for any frequency response analysis, first of all we have to convert from GS to G omega, right? That means you have to put S is equal to G omega. Once you put S is equal to G omega, you will get the sinusoidal transfer functions, right? So once you get the sinusoidal transfer functions, so that will be having two parts. One is known as magnitude, one is known as phase, right? And this magnitude and phase, the variations here in Bode plot, what we will do, we will get a graph like this. So this is your frequency, and in the same graph, I repeat, in the same graph, in the upper sections we will vary the frequency and check the magnitude response characteristics, and in the next part we will having the change of frequency, and corresponding to that we will observe the change of phases, right? By this is a kind of graph where actually this is a single graph, and in this single graph we will have to find out for the same frequency range how this magnitude and phase are getting changed, and this relationship between this phase and magnitude we will find out the stability. Now how this graph will be done, that is the questions, and the question is answered with some of the theories background of it, which will actually clarify your questions, right? The next question is that this a millimeter graph paper will be sufficient? So normally we know there is a millimeter graph paper where x-axis and y-axis, both the axes are linear curve, like this. That means this is this is linear graph, and this side also linear graph. But in case of Bode plot or Bode diagram analysis, we have to take certain another kind of graph, which is normally known as semilog graph paper. Semilog graph paper, right? So normally the millimeter graph will not be sufficient or will not be possible. It is not possible to find out the Bode diagram or Bode plot on millimeter graph paper. So in that case you have to go for one semilog graph paper. And what is the function of this semilog graph paper? By this term you know this is semilog. You can definitely know the term log. So log means actually whenever a large range, for example say 0.001 to 10,000, this is the range of your, say for example x-axis of any graph. So does it possible to include all these points 0.001 to, say for example 10,000 in a millimeter graph paper? No, this is not possible for any graph paper, because you have to scale the axis, right? Scale the points on the axis. So in that case this whole range is not possible to include in the millimeter graph paper. So in order to have this large scale to be fitted in any graph paper, what is the method you will use? That is log. So you have to take log on these large values, such that you can get the total range is reduced. That is why this is known as the log graph. Now the question is why this is semi-log graph paper? Because here we see if this is your actually graph, the nature of the graph where the frequency versus phase and frequency versus magnitude will be plotted. Here we see this frequency axis, this axis is your logarithm axis, this is log scale, and here this magnitude and phase will be linear in nature. So the graph where one axis, normally x-axis, is logarithmically scaled and y-axis is linearly scaled. So that is why this is not the log or normal log graph paper. This is kind of semi-log. Semi-log means one axis is actually done or placed in logarithm scale, and y-axis is normally placed as millimeters, there is linear scale. So this is called the semilog graph paper. So before going to discuss how the Bode plot is done and what are the theories behind it, we will discuss the concept of semilog graph paper. And once you understand the concept of semilog graph paper, then definitely there are some tricks which I will discuss, and by using that you will get the idea how to draw the Bode plot, and from the Bode plot how to get the the stability of the system, right? So here I'm going to just draw one semilog kind of graph paper, and in future when I will discuss this thing, definitely your mind must be focused to that graph paper which I'm trying to draw here, right? See, this is what is known as semilog graph paper. This is I can say this is the semilog graph paper. You will see, and graph paper will be available in your nearest bookshops, where you will find the x-axis. Say this is x-axis. X-axis, there are normally 5 divisions. Normally 5 divisions or 3 divisions are available. Okay, so here I have considered one 5 cycle semilog graph paper. This is 5 cycle. So 5 cycle semilog graph paper we have considered. So 5 cycle semilog graph paper, that means this is your starting frequency. This will be used as the frequency axis, right? This is the kind of semilog graph paper. We will see there are 5 this is bold line like this. So this is one cycle, this is one cycle, this is one cycle, and so these are known as cycle 1, this is cycle 2 and cycle 3, this is cycle 4, and this is cycle 5. So this is known as 5 cycle graph, right? So where you can have any value here. So this should be your origin, but in case of logarithm graph there is no 0 because this is logarithm graph. So and this cycle 1, cycle 2, cycle 3, cycle 4, cycle 5, what does it mean? That means actually if this value you treat as 0.01, say initial value is stated as 0.01, so the next value will be 10 times of that. Next value will be 10 times of that. So if this is 0.01, this will be 0.1, right? 10 into 0.01, that means this is 0.1, and next value will be just 10 times of the previous one. So this is 0.1, that means this value will be 10 into 0.1 means 1. If this is 1, then this is 10. See, the the values are getting just 10 times. So that is 10. So next value will be 100. If this is 100, this value will be 1000. So in this graph we have covered the frequency range from, say for example, 0.01 to 1000, right? For in a 5 cycle graph, right? So I repeat, this cycle 1 means from this position to this point, the value in the x-axis will be just 10 times of the previous one. If this is 1, you can take it as 1, no problem. So this is 1, this is 10. So 10, this means this is 100, this is 100, this is 1000. If this is 1000, this is 10,000. If this is 10,000, that is 1 lakh. So in this axis, the logarithm axis is like that, and in between you will find there are 10 divisions. So if there are 10 divisions, that means if this is 0.01, next is next part will be 0. That is marked here. Actually in the real graph you will see there is a mark like this, right? So this is 0.01, that means this point will be 0.02, this point will be 0.03, 0.05, 0.06, 0.07, 0.08, 0.09 and 0.1. If this is 0.1, again there will be a mark, that is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. If this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. Is 10, that means this will be 20, 30, 40, 50, 60, 70, 80, 90, 100. This is 100, that means this value will be 200, 300, 400, 500, 600, 700, 900, 1000, right? So this is the concept how the x-axis, that is this horizontal axis in the your semilog graph paper, it actually represents. And here you see this is linear scale. Linear scale, that means there are divisions, and any one division we will consider as the 0 dB line. Because already we know in the first half, that is the upper part of the graph we will consider for magnitude part, and these sections we will consider for the magnitude part. This is for magnitude, and these sections we will consider for phase, right? In a single graph we will have to plot this frequency versus magnitude and phase. So this is kind of graph will be available to you. Now the thing is that one most important part I will like to show you, that any line which is considered at the 0 dB. 0 dB line means actually magnitude will be expressed in dB and angle will be expressed in degree. So this is your 0 dB line. Any line is considered in between as your 0 dB line, right? So this is your 0 dB line, and we will divide this linear scale in such a way such that this to this point is 20 dB. Change in magnitude is 20 dB. Either negative side, that is minus 20 dB, either positive side, that is plus 20 dB. So this is 0 dB, means above of this there will be 20 dB plus 20 dB. So upper point of this will be plus 40 dB and upper point of this plus 60 dB. And in lower sections the same type of graphical representation of this point, that means linearly placed points are there, where you will get this is minus 20 dB, this is minus 40 dB and minus 60 dB. So if you just plot this graph or scale this graph starting from plus 60 dB to minus 60 dB, that will be sufficient for any kind of problem we will face to solve, right? For any kind of problem, this minus 60 dB to plus 60 dB and in between there is a 0 dB, that will be sufficient to describe any system. And here in the phase sections you see you have considered this top value of this graph is 0 degree, and from 0 degree in downward directions I have considered as scaling is done like this is minus 90 degree, this is minus 180 degree, this is minus 270 degree and so on. So 0 to minus 270 degree will be sufficient to describe any system phase, or for any kind of systems will be given to you. And in all the cases we will consider this initial frequency as 0.01 radian per second and final will be 1000. So this is our standard graph, where in every case we will follow this structure, right? So 0 dB plus 20 dB plus 40 dB plus 60 dB minus 20 dB minus 40 dB minus 60 dB, right? This is the magnitude sections. And from 0 degree to minus 270 degree in the downward direction, this is your phase sections. And this frequency axis, which is the logarithm axis, where the initial value of frequency, that means this value is taken as 0.01, or you may call it in some cases, if you feel, you may take it as 0.1 also. If this is 0.1, so accordingly these all values will be changed the 10 times of this. And as this value and this value related by a decade, this is known as kind of decade. What is this? It is known as decade. Decade means 10 times. So this concept in used here, which is decade. Now we will discuss the concept of slope. Slope means basically when we draw any straight line, right? We will draw defined straight lines here. So say for example in this the sections, just come to this point. See, I will draw some lines. So this is the frequency. This frequency to this frequency, what is the change? 10 times. That means this is known as 1 decade. 10 times means 1 decade, right? This is known as decade. So we see how to draw the slopes, because these slopes are very important in case of Bode plot, and I will discuss in detail later on. Now see, if you draw this point to this point, say, right, this is a straight line. What is the slope? This is the theta. So slope means what? Change of this magnitude by change of frequency. Change of magnitude by change of frequency. Try to understand what I am trying to discuss. That is, I can see this change of magnitude is this, change of frequency is this, right? So if you draw all these slopes like 0 dB to 40 dB, 0 dB to 60 dB, 0 dB to minus 20 dB, 0 dB to minus 40 dB, 0 dB to minus 60 dB. So how many graphs or straight lines we have drawn? We have drawn 1, 2, 3, 4, 5, 6, and in every case you see change of magnitude. Try to understand the change of magnitude in every case. What are the change of magnitudes? This is change of magnitude means, if this is slope positive, that means plus 40 dB. So this is 0 dB to plus 60 dB. So 0 dB at this frequency, and at this frequency the slope magnitude is 60 dB. So what is the change of magnitude? 60 dB. So 60 dB for this, 60 dB is the change of magnitude by change of frequency. What is the change of frequency? 1 decade. Change of frequency is 1 decade. That means what is the slope of this line? This is plus 60 dB per decade, right? So this is plus 60 dB per decade. That means for a unit decade change in the x-axis, that means frequency, what is the change of magnitude from 0 dB to 60 dB? So this is the change of magnitude. So that slope corresponds to plus 60 dB per decade. Similarly, if you say consider this line, what is the initial magnitude? 0 dB. What is the final magnitude? This corresponds to minus 20 dB, right? So what is the change of magnitude? Change of magnitude is minus 20 dB. This is minus 20 dB, right? If this is minus 20 dB, then corresponding to that slope is minus 20 dB and frequency is 1 decade. So this is minus 20 dB per decade. So what is the slope of this line? Slope of this line is minus 20 dB per decade. Similarly, you see there is a change for this line. For you can say this is the line. Consider this line. Here initial magnitude was 0 dB, final magnitude was minus 40 dB. So change in magnitude is minus 40 dB, right? So change in magnitude is minus 40 dB. So minus 40 dB per decade, right? So similarly, this is minus 60 dB per decade, and this is having slope of plus 20 dB per decade, and this is having plus 40 dB per decade. That means in each case the change in frequency is 1 decade. So this is your tan theta. Tan theta means this is your change in this part, y-axis change and x-axis change. So change in y-axis, it means initial value to final value. That means this is 0 to plus 20. So change in magnitude is equal to plus 20 dB, and corresponding change in x-axis, that is 1 decade. So the slope contribution of this straight lines I have already drawn is having the defined values like plus 60 dB per decade, plus 40 dB per decade, plus 20 dB per decade, minus 20 dB per decade, minus 40 dB per decade, and minus 60 dB per decade. So this understanding of change of slopes or drawing of the slope is very much important when you are going to get the Bode plot, right? Now see, why to draw this graph? because slopes. These slopes are very important because you see, within this complete range of graph paper, you see, whenever we will move, say for example, if I draw a line which is parallel to this line, just I am trying to parallel line anywhere we can draw this parallel line. That means this is the line. This line, if you extend like this, extend in this direction, that is, this is just parallel to this line, right? So this line is parallel to this line. So this line will be having slope of, what is the slope? The same slope, that is plus 20 dB per decade, right? So wherever you will draw this line, say for example, I am drawing this is line, this is the line, say this is the line having slope of minus 20 dB per decade. So if you draw a line parallel to this anywhere, if this line is parallel to this line, if this line is parallel to this line, if this line is parallel to this line, so all three lines are parallel to this line. If it is done, that means each of will be having of slope of minus 20 dB per decade, right? So actually, what is the purpose of drawing these slopes? Because in every case we are going to get only the parallel lines. Once a reference slopes are drawn at the rightmost cycle, we will draw this structure at the rightmost cycle of any graph, right? Here actually, for example purpose, we have shown this here. So we will draw this structure here, right, at the rightmost corner, and this space is not actually usable, and in your actual graph this place will not be used. So you will draw this all these slopes here, right? And whenever you will require any slope, like say slope is required plus 20 dB per decade, so what we will do, we will just take the parallel line of that sections to anywhere in this graph. We can place the same parallel line to this, and it will be indicated that its slope is plus 20 dB per decade. If you take the parallel line of minus 20 dB from this from here, so you will get the minus 20 dB line anywhere if you just get the parallel line of it, right? So that is the concept of this slope. And the decade means this is one decade again, this is one decade, this is one decade, anywhere you can draw these graphs. And just you have to remember what is the change of magnitude. If the change of magnitude is 0 to 20, that means plus 20 dB per decade will be slope. If the straight line is drawn such that there is a slope change of say for example minus 20 dB per decade, that means the magnitude has to be shifted from 0 dB to minus 20 dB. So that is the concept. Now the concept of semilog graph paper is, I think, clear to you, and this is the way how we draw the Bode plot. Now coming in the next class, we will discuss how the actually Bode plots are made.